Yeah, so thank you for the organizers for having me. Thank you for still staying here and I don't know, deferring your lunch. Yes, so I'm going to talk about moire materials. This is a new class of materials, and that I think is the most closely related thing of the things I've worked on that I can offer on a section that is on adiabatic theory and KEM. I'll try to explain maybe where the connection might be between these things. Okay, so
what's the red bit on your first slide?
The red bit? Yeah, that's a good question. What is that? That is the Scottish name for Edinburgh.
Nice.
Do you know how to pronounce it though?
No, I was a bit. It's what is it? Axel Grave over an E, and you know, over you, I don't know. But I don't know. Maybe. So it seems like we do. We have any Scottish people here? No, right? So yeah, maybe we can make friends with the people in the department, and then. Okay. These are my collaborators. Obviously, I'm not going to talk about everything related to that, but these are the people that have contributed to it. And maybe I'll come back to that when the time comes. I first want to talk about regular graphene. Actually, at ETH, someone actually showed me in a lab that even nowadays, graphene, the honeycomb lattice of carbon atoms, it's still you still get it the way it was done in 2004. So you take graphite, you take your Scotch tape, and then you get graphene, and it's still how people do it nowadays in the lab. I thought maybe there's something more advanced, but no, this is currently the way. At least, I don't know. We don't have the most advanced physics lab in Zurich, but this is still how it's done. Okay, this is these are some applications. Nia and Jana sent me at some point a photo of her husband having some shoes where it says with graphene enhanced rubber. So yes, so apparently graphene is now has made it from 2004 just something in a lab to something that is used in daily life. I don't know how expensive these shoes were, but yeah, so this is yeah, this is sort of how far we got. I think nowadays mostly it's used in, I don't know, for, I would say, for industrial purposes, maybe not so much, I don't know, in our daily life. Apart from this was really a nice surprise. We have also some honeycombs in our hotel. And what is interesting here is that we don't have actually just honeycombs, but we have some kind of stacked honeycombs, right? If you see, we have here the hexagonal lattice, and then we have, it seems like we have some kind of hexagonal lattice on top of that. And this is what I'm going to talk about, some kind of not just regular graphene, but stacked layers of graphene, not just stacked, but I'm going to talk about, and these are the moire materials. I'm going to talk about, you have, let's say, graphene, you put it on top of each other, and then you do something to this other lattice, okay? You might either strain it, you might rotate it. So here we have a strained lattice, and then we have a lattice below, then we have a rotated one, then we have 3 rotated ones. And what you see are these large honeycomb patterns forming. These are the moire patterns, okay? So this is where the name comes from, okay? So this is something you can do. You see here, maybe this is a one-dimensional object. This is a two-dimensional, but here you see the periodicity is one-dimensional. Here it's high-dimensional, maybe even not clear if it's periodic or not. Something else I want to just briefly mention, because it, I don't know, it has maybe made it into some kind of physics, I should say, yeah, into some kind of physics newspapers recently. TMDs, what are TMDs? So graphene is a semi-metal, okay? Maybe I can say in a few seconds more about it. TMDs are semiconductors. TM stands for transition metal. Okay, these are these in the periodic system. These are the elements you would find here. Let's say tungsten would be an example of that. And then we have the chalcogenides, for example, sulfur is one of them. And then TMDs means that you have one transition metal and 2 of the chalcogenides. And so, for example, this kind of honeycomb structure is a TMD, okay? And so you might say, okay, that's interesting looking, but is there anything one gets out of this? So I think because mainly quantum information theorists, people are here, so you could say like, okay, why should I care about this particular stuff? Well, okay, so we see here, so this is from an experimental paper. This was the first experimental paper where actually superconductivity was measured in this twisted bilayer graphene. Okay, so you have it, you rotate it. There's a certain angle where you measure superconductivity. This I don't know if you know what this is. This is from 1980. This is the first measurement of the quantum Hall effect by von Klitzing, the notes in his book. So and how is that related to the things that we're looking at? Well, okay, so there was this measurement of superconductivity in this twisted bilayer graphene at an angle 1.08. Okay, that's called this magic angle. That's why it's called magic moire materials. Okay, and then we have something interesting, which is the fact that TBG has been shown to be a churn insulator. Okay, insulator, well, churn, I think these two words, they don't give you a good idea of what it is. It means you have a quantum Hall effect, but without an external magnetic field, okay? So you have a non-zero churn number appearing in your system, okay, without applying an external magnetic field, okay? And so I mentioned these TMDs. So it turns out that they, and this is very recent, they've been shown to be fractional churn insulators. So you see the fractional quantum Hall effect. So you see some kind of anion statistics in these TMDs, but the point is, again, without an external magnetic field, right? Usually when you want to measure the fractional quantum Hall effect, you have to apply very strong magnetic fields. And the point is somehow that in these materials, it works without a magnetic field, okay? And in some sense, this has to do with the fact that the Hilbert space here is intrinsically complex. So because we have these Hamiltonians we get, they have complex numbers, and that allows for these non-zero churn numbers. And maybe I can say more about that at some point. So here, this is maybe another, I don't know, application of the fact that Hilbert spaces are usually complex. I want to talk mostly about this graphene because I think it's the simplest model to study in mathematics. And so I discarded TMDs. I just wanted to mention them because I think they are, well, it's interesting that this is possible. Okay. So graphene in the simplest way is just described by Dirac operator. Okay, so it's really the, okay, if this doesn't mean anything to you, just, think of, there's this graphene, this layer there. It's described by Dirac operator, okay? If you have two of them and they don't talk to each other, right, two graphene sheets, you might say, okay, well, then I have two Dirac operators, right? What else is there to say? And then the spectrum that will describe these two layers. Obviously, that's not the end of the story. The two layers, they talk to each other. The electron, it can sort of hop from the upper to the lower layer. And so you want to have some kind of tunneling effect, okay? And this tunneling effect, so this is a 2x2 matrix, so just based on sort of matrix dimensions, you might say, okay, if you want to describe the tunneling, it means you can go from here to there and the other way around. So you have to put some kind of 2x2 matrix there. Okay, and it's tunneling potential, and it has this kind of larger, so when you twist them, these sort of moire structures, that's sort of described by this here, okay?
To fix the ideas, this is the Dirac operator of the graphene lattice.
So the Dirac operator, well, so you should think of this as, question maybe where does this come from, this model? In some sense, it's, if you have a tie binding model, right, a discrete model of this, then if you look at the energy limit around zero energy, okay, if you take a low energy limit, you recover the Dirac operator, so then it's a continuous model, okay? So it's a low energy limit because what we are interested in is the electronic structure close to zero energy, and that's where this comes from. So the continuous model, it doesn't really see the honeycomb lattice anymore. Well, in some sense it does because of the tunneling, but that's where the Dirac operator comes from. It's some linearization of the tie binding model. Okay, this is the tunneling potential. So, okay, our entire Hamiltonian is described like this. It's called the Bistritzer-MacDonald Hamiltonian. Bistritzer-MacDonald were sort of the first people to write down a model for this actually before this entire thing about superconductivity came up, okay? Which was actually rather recent, okay? And so this is the entire Hamiltonian, it's 4x4. It has a differential operator in there and some kind of tunneling matrix. In particular, this is a periodic Hamiltonian because it turns out this tunneling potential, you saw these larger honeycombs forming, right? So this is a periodic structure somehow, okay? Periodic differential operator, that's somehow we're going to study. This is what I'm interested in. There's some derivation of that model as well. Maybe we should mention this in physics literature and then also in the math literature. Well, in order to study this, there's one thing one does. One does a rescaling. So you see this matrix here. So the most tractable way in which you can write down this model is that you set the diagonal terms to zero. Okay, that's an approximation that is somehow justified because they are a bit smaller than the off-diagonal ones, but it turns out that this is mathematically the way you want to go. And then you do rescaling that you say theta z, which was in here. Theta was this twisting angle between these lattices that goes over to z. So, okay, by some rescaling of the z coordinate, you get that your alpha, the parameter in front of you, is now proportional to 1 over theta. Okay, so alpha is the parameter we will talk about from now on, and you have to remember it's somehow inversely proportional to the twisting angle. Okay. Okay, so this is somehow the model that we're interested in. And this model has been proposed in this paper, which is now, I think, a bit the standard for, if you want to do some ab initio analysis in this business. It's called the origin of magic angles and twisted bilayer graphene. And it proposed this model. Okay, so by doing some rearrangement, so you just multiply by a certain matrix, you can write the entire Hamiltonian in this nice off-diagonal form, okay, where here's this tunneling potential U appearing, and here we have 2 times the Cauchy-Riemann operator. Okay, so anti-holomorphic derivative. Okay, and so this is the Hamiltonian. Okay, so what you should maybe remember is it has this nice off-diagonal form. It's the alpha. It's really not, I don't know, self-adjoint at all. And then you have this tunneling potential. Well, okay. Essentially, it has to satisfy 2 symmetries, right? Because when we have this moire pattern, we see, okay, this is somehow periodic, okay, at least sort of 2 leading order for us. And we can maybe discuss later what quasi-periodic effects would do here. But 2 leading order, it looks periodic to us. And it also has the honeycomb lattice symmetries, which is that if you rotate it by 2 pi over 3, then it's essentially left invariant. Okay. And okay, so this is sort of incorporated here. So this is somehow the periodicity. This omega here is the 3rd root of unity. So in some sense, there's a periodicity condition, okay, up to some phase. Actually, this phase turns out to be important. This phase comes from some considerations that if you have 2 sheets of graphene on top of each other, you have certain orbitals that talk to each other. These orbitals have some complex numbers in their wave functions. So these hopping elements, they will be in general complex, and that's how these things, where they come from. And this rotational symmetry, okay, so we have a translational symmetry and a rotational symmetry. That's because when we twist that, we get this large honeycomb structure. Okay, so this is what this really means. Okay, and this is the simplest potential that satisfies these 2 symmetries. It looks like nothing, I think, when one sees it the first time. Or it looks like maybe some Fourier polynomials, and it's not clear, but it's somehow the simplest expression you can write down, apart from maybe 0, that satisfies these 2 things. Okay, so that's the idea. Okay, so this is the Hamiltonian. This is the potential. Maybe remember this off-diagonal part, or this the alpha in this Hamiltonian. That's the crucial bit. Okay, and so since this Hamiltonian has this off-diagonal structure, it also means that the spectrum is somehow symmetric with respect to 0. Okay, so this is the off-diagonal operator I'm going to look at now. And alpha, this parameter, was proportional to 1 over the twisting angle, right? This was somehow where it came from. And now we want to study the spectrum of the alpha. And I'll show you in a second animation for that. So as alpha moves, the spectrum is always a discrete set. It stays the discrete set, and then at certain points of alpha, it becomes the entire complex plane. Okay, so the spectrum, even though the operator depends nicely on alpha, the spectrum does not depend nicely on alpha at all. Okay, so the spectrum is very discontinuous in this parameter alpha. And of course, only possible because this operator is not self-adjoint, right? This operator was self-adjoint, and you have such an alpha dependence, the spectrum would also change in a very nice way. Okay, so this is what we have. So this is a constant figure. We plot the spectrum of the alpha. Okay, it's in a certain window here. It's always a fixed set of discrete points, and then for certain values of alpha, alpha being raised to 1 over theta, it's the entire complex plane. And as you might guess, since there's this connection between alpha and theta, these turn out to be the magic angles where the spectrum is the entire complex plane. That is sort of what we will see, and I'll explain where the connection is. So to me, this kind of effect that a spectrum can change in such a dramatic way was not known, I think, before I started working on this. There's a simple example where one can see this fact explicitly by just solving an ODE. It's just this nice example by Bob Seeley. It's a simple first-order differential operator, so you can just solve an ODE and convince yourself, oh, it's really like that. So the spectrum, even though this operator depends nicely on alpha, the spectrum is either the complex plane for the integers, or it's empty otherwise. Okay, there's no eigenfunction. Because you somehow violate a periodicity condition that you would have to have, and so there's nothing in the spectrum anymore. Okay, so what is it that we are looking for here when we talk about this twisted bilayer graphene, when we talk about these effects? It's strongly correlated electron physics. Okay, so that means that what I have to think about when I talk about this model is I have to think that this is some kind of sort of effective 1-particle Hamiltonian, and on top of that, I want to put my electron-electron interactions, okay? So there's not just one electron in this material, but many, okay? So this is somehow the kinetic energy, if I want to think about it like that, the Hamiltonian we have here. And what I want is that the electron-electron physics really dominates, okay? So what I'm looking for are sort of zero eigenstates, so having a lot of zero eigenstates of my Hamiltonian. That's maybe the sort of mathematical terms at first, how you would formulate this, okay? So if I want to have something like that, effects where, you have, I don't know, superconductivity or a quantum Hall effect, it's really, how should I say, it's really about having an electron, the kinetic energy of an electron really confined to a constant value 0, let's say, in this particular case, or to something constant in the case of the quantum Hall effect. Okay, so if I have a periodic Hamiltonian, there's one reduction that sort of everyone either knows or maybe doesn't know, but if I have a Hamiltonian, and I've never taken a course on sort of solid state physics, there's the Bloch-Floquet transform that transforms the Hamiltonian, which is originally defined like this on this space, right? Because of the differential operator on the plane. So it's defined on this space. I can pull it back to a Hamiltonian on one fundamental cell of my moire lattice, okay? But the price I have to pay is I get a new parameter, which is called the quasi-momentum in this business. And I have to, if I want to understand the spectrum of this guy, I have to understand the spectrum of the one on the fundamental cell with periodic boundary conditions for all quasi-momenta k. Okay, so this is one transformation. It's essentially a Fourier transform that one has to do in order to study this. Okay, so I get a Hamiltonian. When I carry out this Bloch transform, I get this Hamiltonian here. It's essentially the same Hamiltonian, only that it now acts not on this space, but on the fundamental cell. And I have this new additional parameter k here, okay? And if I want to know the spectrum of H alpha, I have to know the spectrum of this guy for all alpha, okay? And now let's reformulate this thing that I said before. What are we looking for? Well, we're looking for a lot of zero eigenvalues. So if zeros in the spectrum of HK alpha for all k, okay, if this is our condition for a magic angle, then this is equivalent to saying that k is in the spectrum of all the alpha. Okay, so a flat band, the sort of the union of the eigenvalues of HK, okay, is called a band. And then a flat band at energy 0, which means a magic angle, means that the spectrum of the alpha is the entire complex plane. Okay, so that is the mathematical condition. I want to understand, when does this operator have the entire complex plane as a spectrum? This is what I was plotting, right? This discrete set, and then at certain values, which became the entire complex plane. So the question is, for which values of alpha does that happen? And so if I plot, this is the complex plane, so this is the real axis, this is the imaginary axis, then this we will show, well, we'll not show it, but we will see how one can deduce that this is the set of alphas for which this holds. Particularly as a discrete set, it looks very structured, and the ones that one is interested in are the red dots on the real axis, okay? And the question is, well, it looks like a bit of an implicit question, right? How can I figure out if this is the entire complex plane? At the moment, we don't have a tool to study that question. So how can I make such a figure? That's maybe the question at the moment. Okay. So here you see the bands. So here you see alpha moving. Now it became flat at energy 0. Okay, so these are the eigenvalues of my Hamiltonian, parameterized by this parameter k. Okay, real part of k, imaginary part of k. And then you see, as alpha moves, there are certain values where this lowest band becomes entirely flat. And it's energy 0. I only plot the upper energies because I have the symmetry in my Hamiltonian. The negative energies are the same. Okay, now I see, now it's a bit difficult actually to see because there seem to be more and more bands coming down, but maybe the first one was very pronounced. So this first one, maybe if I go back again. So here, the first magic angle where this band becomes entirely flat, maybe that was kind of clear. Okay, so that's on the Hamiltonian level where this condition comes from. Okay, why I get there strongly correlate electron physics effects. Okay, so I said, okay, the question is somehow, how can we characterize these magic angles? Well, the way to go is that we want to have a spectral characterization of them. So we're interested in our Hamiltonian, just to say it again, with some sort of periodic boundary conditions. So this is the translation by this operator LA is the translation by the lattice, our moire lattice, and then we want periodic functions. The bands that I'm talking about they are the union over K of the individual eigenvalues of my Hamiltonian. And as you saw maybe in this movie before, there are 2 points where I always have my 2 Dirac points. And so maybe it's actually visible in this steady picture, but this is for alpha 0.3, there are always 2 Dirac cones. You see the upper part, the lower part, you have to imagine because I'm just plotting positive energies. But yeah, so these are always, these stay always at the same points. Okay, so the first theorem that we then actually proved was this dichotomy, so that there exists a discrete set such that the spectrum of the alpha is either related to the dual lattice of the moire lattice or the honeycomb lattice, plus these 2 Dirac points, so it's shifted by these 2 Dirac points, they are 0 and minus I, or it's the entire complex plane, and that's true for a discrete set. And that's the first theorem we proved about that. So this initial movie that we saw is true. And moreover, and that's maybe the more interesting part here, there exists an operator tk. Okay, so I choose a k which is actually not in that set. In that case, I can look at this inverse and the eigenvalues of this operator, this compact operator, right? Because you have an inverse differential operator here and you have this periodic potential, so that's why it's a compact operator. The eigenvalues of that turn out to be the magic angles. Okay, they're independent of k as long as I choose k, as long as this object essentially makes sense. Even though it looks like, as I weigh k, maybe the spectrum of tk should actually change, but it does not. And the magic angles, they turn out to be exactly these values of alpha, okay, where the spectrum of this operator tk is. Okay, so this is somehow an explicit condition for where the magic angle is, okay? And somehow finding this operator on the fact that it's independent of k, it's somehow connected to this condition here, okay? I thought I would have to talk right after 2 other talks, so I thought, okay, maybe I shouldn't really include proofs of these things. Yeah, so I'm skipping proofs here, but this is sort of the characterization of these objects that one has. Interesting, another interesting feature about all this is that you saw when alpha is large, okay, so for small twisting angles, so you have these 2 sheets, you have a very small twisting angle, then you see that there are a lot of bands that look almost flat in this business. Okay, and well, a lot of bands that are almost flat, that's not really good for our strongly correlated electron physics. Because that means that our electrons can actually move easily from one band to the other. It's good to have this flat band and then a large gap, for example, for the fractional quantum Hall effect. That's essentially the idea of Haldane, right? That you have these large gaps between the Landau levels, and then you kind of know what the wave functions there look like. And it turns out, so for small twisting angles, we shouldn't expect too much, and that's formulated maybe in this theorem. So there are, as alpha is large, so this is an asymptotic result for large alpha, so small twisting angles. There are essentially alpha many bands that are exponentially close in alpha to 0. Okay, so a lot of, essentially, I have, if alpha is 100, I have 100 bands that are e to the minus 100 close to 0 energy, right? That's somehow the statement of this result. And that uses, okay, maybe this is one thing I say. So this uses some kind of ideas of that go back to solvability of PDEs. It's related to, I don't know, quasi-modes. So it's essentially related. So the techniques come essentially from the question, you know, if I have a PDE, a linear PDE with C infinity coefficients, when can I locally solve such a PDE? And there, Hoymander developed some techniques to construct certain quasi-modes, and that is essentially what enters in this proof. Okay, so somehow not that directly related, but at least at first glance, but that's sort of what underlies a bit this idea. So there's a certain condition that, in terms of the Brasson bracket, that allows you to determine whether a linear PDE has a local solution, and that's what enters in the proof here. Because it allows you to construct quasi-modes, and these quasi-modes are then what's used to show this exponential squeezing. Okay. Okay, so this is this. So this somehow has another effect. So you have to understand that for this twisted bilayer graphene, I showed you the magic angles. It seemed like there are infinitely many, but in experiments, people only measure one. And so I said, okay, maybe there's this squeezing effect here. A different way of formulating this is that since we had this characterization, Hamiltonian has a flat band at a twisting angle alpha, so alpha being 1 over the twisting angles, 1 over theta, equivalent to the spectrum of this being the entire complex plane, is equivalent to being 1 over alpha being an eigenvalue of tk. And so I can ask myself, what happens with the spectral stability of this operator tk, right? That was a compact operator. I took the inverse of the Cauchy-Riemann operator minus k, and then I multiplied it with these tunneling potentials. And what happens there is that, so this is the figure, right? These are the magic angles. This is if there's no noise, okay? Now what I can do is, and I just put here the definition of the pseudo spectrum just to, remind you what we are now going to see. So if I take a small random perturbation of my operator tk, I just randomly perturb my potentials by a bit. Okay, now you're going to see sort of snapshots for different realizations of the noise. And then what you see is that the first one here is pretty stable. Okay, we see these iterations. So the eigenvalues here are all over the place. Okay, so the eigenvalues of tk, they fill everything essentially because they're not stable, the large ones. Okay, the only stable ones are the first ones. And that's related to this exponential squeezing effect. Essentially, it's just a pseudo-spectral effect of our operator tk. Since I have so many bands, small perturbations can move the magic angles by quite a bit. Okay, so somehow that is somehow an explanation for why in experiments you maybe only hear about this one magic angle where people measured the superconductivity. Okay.
But also the second one.
That's right. That's right. So I mean, yeah, you can say that, yes. You can say that, okay, maybe this one also looks stable, right? But there's a clear idea of sort of larger ones maybe being not so stable, right? Yeah, so there are actually also, since you're saying it, there are actually papers talking about the second magic angle, but then it's never. The first one I think is that one is for sure established. But there don't seem to be infinitely many. Maybe that's what I could say with certainty. Okay, so the question is though, I mean, okay, we have this characterization, right? You're a magic angle if you're an eigenvalue of this compact operator. But mind you that, in general, a compact operator like your Volterra operator, right? It can be that it has only 0 in its spectrum. So that can happen for a compact operator that's not self-adjoint or not normal. Also, right? You're not 0, but you only have 0 in the spectrum. The question is, why does this not happen for this tk? Okay. Let alone, we did not prove initially, at least, that there's a real magic angle, which are the ones that one is interested in, right? Maybe you could show there's an eigenvalue, but then it could be this one or something like that, right? And of course, this extends everywhere into the complex plane, this figure. Okay. So how do we first show that there is a magic angle? Well, so the trace, that's always true. The trace is the sum of the eigenvalues, as long as the operator is trace class. So we computed the trace. We have to raise it to the right power, that it's trace class, and then we get this number, 72 pi over square root of 3. And then we knew, okay, it's not 0, so there's something. Okay, now it could be that there are two complex ones that just cancel each other, give us a real value, and there's no real magic angle, right? So somehow we haven't really proved any of these. We just proved, okay, something is there. Then there was a computer-assisted proof. Well, okay, so if you have a computer at your hands, right, you can use some, especially if you're a compact operator, you can do some kind of finer truncation, you estimate the tail, then you show, okay, there's something. So this is essentially okay, it's not, I don't want to trivialize that result, but this is essentially the idea how you have a computer-assisted proof of such a thing, right? Because estimating the tail is also non-trivial for a non-self-adjoint operator, but this is how Laskin and Watson were able to show that there exists a real magic angle.
You guarantee it's real?
Yeah, I cannot from this, right? It's at the moment.
Like the stale argument, how do you guarantee that?
So okay, this is a good question. So the thing is that what you can do, and this was why we also computed trace. So we had the determinant in mind. Okay. Then you can easily see from the symmetries that all traces have to be real. So the determinant on the real x is actually a real function. And then if you show, okay, you have a real function, you prove it has a 0, or some kind of truncated thing, then you can say by some approximation scheme that, okay, if this one has a sign change, just intermediate value theorem in some sense. If this one has a sign change, then also the original thing has to have a sign change. Yeah, so there's another trick here involved, because otherwise it would be hard, right? If you would not have that. Yeah. Yes, so this is how this worked out. But so the only thing, I mean, that was missing here for us was that, other traces were difficult for us. just the way we compute this power, it was not accessible for higher powers. So then we got some help. And then we had by Tristan Humbert, and he was able to show the following, that not just if you raise it to the fourth power, but if you raise it to any power, essentially, once it's trace class, the sum of the traces is pi squared of 3 times a rational number, okay? And he has a formula that essentially says, okay, if you have, I don't know, the 10th power, then, okay, it's given in terms of some residues. You cannot really, I mean, you can, but you can do it for finitely many, right? For finitely many, you can compute these rational numbers here. These are the rational numbers. It's difficult to, you cannot go at a closed expression, at least at the moment, with what we know, but you can compute as many of these rational numbers as you want, and then it's the Redholm argument trick. But an interesting side remark about this is that if you have a compact operator who has the following property that all the traces are pi squared of 3 times a rational, then it follows automatically just, like a number theoretic property in some sense. If you have numbers that raise to this power always of that form, then there have to be infinitely many of them. That has to do with the fact that pi is a transcendental number, because otherwise you can construct a polynomial that has then something related to pi as a root, okay, with rational coefficients. So there are infinitely magic angles, and there's a real one. That's essentially what you get out of this idea. Okay, so that's a bit the idea. But infinitely many could be complex ones. Okay, and then this is the theorem. So the largest one, we know it's simple eigenvalue, and it's located in there, and there are infinitely many of them. Okay, and then there's an interesting effect that you numerically observe, at least, which is that these eigenvalues, well, they seem to converge to something. Okay, they seem to converge to these magic angles. If you write them down, knowing that maybe they are not as stable due to this pseudo-spectral effect, this exponential squeezing that we showed. But at least if you do it numerically, then you see that, okay, the difference between them, they seem to converge to something slightly larger than 3/2. Okay. These are the first 13, and these are the values. And this was already observed in the physical literature before we did this, just by looking at when does the band become flat. They conjectured 3/2, but maybe this does neither prove nor disprove that it converges to 3/2, but I would say maybe it's slightly above that value. And there is a physics suggestion that says, okay, it should actually maybe be 1.47. But I think at the moment, at least, these larger magic angles, they are not really accessible. And we don't know, right? We were initially hoping that there's some semi-classical analysis can be applied here to show this kind of equidistant spacing, but that hasn't worked out. And it actually hasn't worked out for a certain reason, because when you prove something, let's say like a Weil law, meaning that we can speak for an infinite amount of time because the chair is gone. So
I took over.
Okay. So okay, the reason is the following, right? If you prove a Weil law, then it somehow holds in an equivalence class, right? You have maybe, I don't know, a Laplacian, and then you have some potential, and the potential is bounded, and then it's kind of spacing of the eigenvalues holds for all potentials that are the same equivalence class in some sense. Well, here I have this potential, this moire potential that, my square honeycombs, and then I have this other potential here, right, which has the same symmetry, just that it has higher Fourier modes. Okay, now I can ask myself, okay, do I still have this equidistant spacing or not? And so I have this parameter theta. Theta, I'm sorry for that. Theta has nothing to do with the twisting angle here. It's just my parameter in which I interpolate between these two things. But ideally, I would hope, that, okay, my equidistant spacing of these eigenvalues holds for, for any value of theta, because it's a generic property. So why are there red and blue dots? Red means I'm a simple eigenvalue of tk. Blue means I'm twofold degenerate. Okay. Twofold degenerate just means that 4 bands become flat. Red means 2 bands become flat, right? One from above, one from below. Okay, so now as I move this, I see, okay, does this look equidistant anymore? Probably not, right? The spacing of the real magic angles, it changes completely, right? It's not protected all in the symmetry class, so it has to be a property of these first Fourier modes, okay? So that's a bit disappointing, but maybe a bit good that, it means that maybe you've not missed something that is super obvious in terms of semi-classical analysis. But there's an interesting effect, right, which maybe we didn't appreciate, at least in our first paper, which was that there are these multiplicities. So the question is, can we say, in some sense, that we only have 2 flat bands or 4 flat bands, and what can we say of how many there are, because it seems like there are always infinitely many of them. And that's something that one can do, actually by a similar consideration. So if you have a tunneling potential that satisfies all the symmetries, then it turns out that, okay, you square this operator tk, if it would have only simple magic angles, okay, now so our model satisfies 2 symmetries. One is a translational symmetry, the other one is a rotational symmetry. Before, this L2 space only had an index 0, meaning periodic functions on the torus, on our fundamental moire cell. Now it has an index j. That's because now I've taken rotations into account, right? I can rotate a function. I can pick up a phase. I can pick up no phase. I can pick up a phase omega. I can pick up a phase omega bar. Omega being the third root of unity. That's because of the honeycomb symmetries. Okay. So that gives me these 3 invariant subspaces of my operator AK. And okay, since the spectrum of TK is independent of K, I specialize to A0. I leave the space invariant. One can show that if all the magic angles are simple, then the traces in the space where I don't pick up a phase when I rotate, where I pick up phase omega, they're going to be 0, because that is where the multiplicities have to be. And I would only have something in the space where I pick up omega bar. Again, I'm not showing you the proof, but it has a consequence, which is that the trace on this subspace, I can write it as 1/3 of my trace on the entire thing, so on L2 0, okay, which was this rational times pi over square root of 3. Then there's a remainder, okay, but this turns out to be a rational number. And again, this implies that, okay, since this cannot add up to 0, I saw that these rationals were non-zero, so this cannot add up to 0. So I conclude that, well, this is actually a bit more of a conclusion. I show that for a generic, it's not just I, but my collaborators and me, we show that for a generic set of real analytic potentials. Okay, all magic angles are either simple or twofold degenerate. And for such a generic set, I can also say then that there are infinitely many of each class. Okay, so you only have these 2 cases. So again, it has something to do with the transcendental properties of pi, that these 2 cases exist. Okay, so this is a bit, what one, well, what I would say is a bit the basic theory of this twisted bilayer graphene about magic angles, at least when it comes to the non-interacting physics. 5 minutes, yes. Okay. Maybe one thing that, okay, so I'll not talk about interacting. I mean, there's a lot to say probably about that, but I'm not going to talk about any interacting parts. They're very interesting, but I'll skip that. I'll talk instead about something, since it's adiabatic theory. So I was working with a model that is somehow periodic, right? And in Platonic reality, I mean, whether it's periodic or not, that's hard to decide, right? Because when you have these twisting angles, these lattices might be commensable or they might not be commensable. In real life, or in this model at least, people assume they are commensable, but that's actually a subtle question. So this effect appears when you go to twisted trilayer graphene. So you have 3 lattices, because then even if you assume these potentials being periodic, once you have 2 twisting angles, and it's no longer clear if this is periodic. It's periodic if and only if the twisting angles are commensable, so if they're rational. Okay, and then all kinds of funny effects can appear. So you have then 3 Dirac cones, right? Because of trilayer, so 3 Dirac cones. At a magic angle, okay, 2 of them disappear, 1 remains. Here you have 2 overlapping Dirac cones, so 1 is hiding in the other. And then again, 1 remains at a magic angle where you have these flat bands at energy 0. Okay, so this is away from a magic angle, this is at a magic angle, we have something here. And okay, similarly, one can show there that for all twisting angles, there are infinitely many magic angles. So I should explain what that means. So before I had my twisting angle here, I did a transformation. I had it in the parameter alpha. So I can ask the question, so fixing zeta 1, zeta 2, okay, these rational commensurable parameters, what are the parameters beta such that, this one exhibits a flat band? And then it turns out that, okay, so there are infinitely many such parameters beta such that this Hamiltonian for fixed zeta 1, zeta 2 has a flat band. Okay, but the question is are they continuous in the twisting angles? You know, that's something maybe you would hope if you would try to do some sort of irrational theory. So if you have non-commensurable angles, the idea for, let's say, all these quasi-periodic operators is that you approximate with rationals. And it turns out, no, this set of beta, so fixing a twisting angle, approximating an irrational number, an irrational ratio, it's nowhere continuous actually. Okay, so there's no way one can understand if there are sort of in the irrational case any magic angles. Also, this thing that it's not gapped, that this magic angle is actually bad, for example, for the fractional quantum Hall effect. It's also not being measured there because there you really need these large gaps. So this is, I think, a really interesting open question that I would be interested in hearing the answer to. I want to explain maybe to you this thing about the fractional quantum Hall effect, since I have about the regular quantum Hall effect, since I have a bit of time, maybe. I'll skip the 2 minutes. That's enough because everyone knows the effect already. So it's just, I have to just explain in my model. So I have this, the alpha here. Okay, and the thing is that I have these Dirac cones. So I have, what do these Dirac cones mean? These Dirac cones mean I always have a solution. Remember that when I do Bloch-Floquet K theory, I get quasi-momentum K, right? And then what protected Dirac cones means is that, okay, of all this, you know, huge set of Ks, I don't know, and the Brion zone, as you know, physicists would say, so in the dual torus, I have these two specialized points. One is 0, one is minus I, at least in my notation here, where I have a solution U such that d alpha U is equal to 0, right? I have one. So this is just uses that I have one protected state. And okay, so if I, okay, what is sort of the easiest thing I could think about, right? Once I have this solution, how can I build other ones? Well, the easiest thing is that, okay, if I just want to solve, this is the equation where I have to solve the alpha minus K, so K is quasi-momentum UKZ is equal to 0. That's what I want to solve. So the easiest way I can do this is I multiply by this guy. Okay, and then remember that the alpha had the 2dz bar operator on the diagonal. So that's actually quite nice, right? So once I do that, okay, if I get down my K, right? My notation with the capital D was that there's a 1 over I, so that I cancels, and oh, I have a solution, right? So this times this is actually a solution to my equation. But it has a problem. The problem is that I'm looking for periodic solutions, right? So if I take my K not in the, not in the boundary of my Brion zone, this function is not going to be periodic. So essentially, because this is not going to be periodic for all K, right? So I have to find a way, okay, to make this a periodic solution. Well, how can I do that? It seems a bit difficult because on the one hand, I don't want this F. It is my correction factor now. Let's say I don't want it to destroy the fact that I have a solution. And that means, okay, it has to not see the dz bar derivative. Okay, so it means that it's analytic. But okay, well, the functions that are periodic and analytic, these are quite boring functions. So so it will not help me to just, you know, take constant functions. So this function fk, it cannot be analytic, it has to be actually moiromorphic. And how this can work is that the poles, because it cannot be singular, the eigenfunction has to cancel with the zeros of this uk. Okay, so that, oh, sorry, with the zeros of u, right? So the way I can construct a solution is that if this u, okay, my Dirac point that is always there, for a certain alpha has a 0, then I can construct a meromorphic function which restores my periodicity and gives me a solution for all k. Okay, so looking for magic angles is somehow looking for zeros of my solution d alpha u is equal to 0. Okay, so here are a bunch of figures. So this is at simple magic angles, I get a 0 at 0, and it turns out that you always get a 0 at 0. And then at twofold degenerate ones, I get a 0 at 0 and another specialized point. So here I get a double 0 at 0, sorry for that. And here I get a 0 at these 2 points and these 2 points. Okay, so they have to be, this is the, oh, these are vectors, right? So I have 2 components. I plot the modulus of them. Zeros, they have to coincide. So here I have a 0 at 0. Here I have 2 zeros there. And here I have 2 zeros that coincide there. Okay, and then I have to prove, of course, that this is what always has to happen at these magic angles. And then the way this, or what this function fk looks like is given in terms of theta functions. Okay, so this is actually a general sort of complex analysis thing. And maybe the first time you see this, you think like, where does this theta function comes from? But it's I think it's a well-known thing that this is the only thing you can take there. And this way you can build these kind of solutions. Okay. Okay. Okay, so if you have a simpler two-fold degenerate magic angle, then the zeros are where they are. But the interesting thing is now, and this is why we can say, and this is why we can say something about Chern numbers, is because we have an explicit dependence on K, right? Now I have my solution U doesn't depend on K, and now I've exhibited this entire thing, it depends on K, and it depends on K, and that's the point, in a holomorphic way, okay? And then I can compute a Chern number, again, referring to the complex Hilbert spaces being necessary in this business. So I have this holomorphic dependence on K, then I can use the Chern connection to compute my curvature. So I'll be brief about this, very brief apparently. So let me just explain what comes out of here. So so this is my Chern connection. It looks like this. Essentially I can use it because I have a holomorphic dependence on K. That's when it works. Otherwise I have to work with this clumsy Berry curvature expression. And here in the holomorphic case they coincide. The curvature is then given by this. It turns out that the curvature, and this is an essential thing. So once you have these kind of Bloch wave functions, that they depend holomorphically on K, unless they are trivial. That means that these two things are linearly dependent. The curvature is always positive, and then because of some I business, you always get a non-zero Chern number. Okay, and so here in this business, you can explicitly compute a Chern number. It turns out to be -1. This is shown for the case of the line bundle. So when you have a simple magic angle, meaning two flat bands, the upper one, there's not a notion of upper and lower, but the upper one will have Chern number -1, the lower one of +1. And in the degenerate case, you have to work with vector bundles, but it's the same computation. Okay, I think I should close here. I skip this and then I finish with my questions. Okay, thank you very much.